Yeah, those machines, we have to buy, pretty high-end machines that have to hold really, really tight tolerances. Some of the tolerances we're holding are pretty crazy. Like, for example, on the zoom cells, we hold diameter tolerance of plus or minus 2 microns, which 2 microns, that's the metric. The inch would be about 79 millionths of an inch. So to put that in perspective, a human hair is about 70 microns in diameter, and we're holding plus or minus 2 on that diameter. So it's really, really tight. You can't even measure that with a micrometer because the pressure of the tool, even light pressure, pushing on that is enough to bend it out of shape and get an incorrect measurement.
Wow.
So we use air gauging, special air gauging to measure that with air.
You measure something with air?
Yeah. Yeah.
So if you were going to get your micrometers out, everybody put them away because we're not using those right now.
Yeah, we're just going to use air, apparently.
Yeah.
How do you measure something with air?
Yeah, so the air gauging we have, it looks like a ring gauge. So it's a specially made. It looks like a steel ring, and it has a hole through it, and that hole is precision ground to a particular diameter, and it has little air nozzles inside of it, and when you put the part inside of it, there's air blowing through those air nozzles, and it literally, through air pressure, it wraps like a air all the way around the part, so it's kind of floating inside of that, and the machine can determine the diameter based on that airflow around the part.
That's insane.
That sounds made up.
You know what I've always wondered? So whoever invented that machine probably had to make it with something very precise. So it's like you're measuring something really precise with something that's very precise. But how do you make something very precise without a very precise tool? And then how do you make a very precise tool without how does that happen? At what point is somebody making a precise tool with like a rock and a hammer?
Yeah.
Does it get progressively more precise as...
Yeah, what did the air guy need to make his thing?
Right.
Well, it actually brings up an interesting thing because first of all of our measurement tools have to be calibrated and certified every year.
Okay.
And then you ask, well, what do you use to certify that? And so there's actually a standard called a NIST standard, and there's like a national, agency that basically they have these gauges and different things that are like highly protected that are
like Fort Knox or something.
Yeah, I mean literally, and that's like the standard. And so, like, for example, one of the things that we have to do is so that they call that the NIST standard. The NIST standard for all of metrology, which is the science of measuring things, is everything has to be at 68 degrees to measure it. Because if your gauge that's made out of metal presumably changes temperature, if it gets hotter, it's going to grow, and if it gets colder, it's going to shrink. And so the tolerances we're dealing with are so tight and so small that microscopic shrinkage or growth of the part with temperature change will affect our measurements. So we actually have to keep everything at a really stable temperature when we measure it.
So like the temperature in the machine shop, I know, for example, when we moved to the new facility here, you guys had to do some special stuff with the HVAC system and stuff like that to keep the temperature in the machine shop a pretty relatively constant temperature.
Yeah.
You do something with the coolant too that jets onto the parts while they're being machined, right?
Yeah,
that has to be temp controlled.
Yep, a number of things. So for one, we have an in-floor heating and cooling system. So we have these tubes that run through the concrete floor that can be heated or cooled. So we basically heat or cool the entire slab that the machines are sitting on. And it creates this giant thermal mass. And so the temperature of that thermal mass, because it's so massive, is really, really stable. It doesn't change very fast. And so that allows us to be able to hold a really stable temperature. And so fun fact about that is we have about 90 miles of tubing in this building for heating and cooling. And according to the engineers who designed and built the building, they said it was the largest heated and cooled floor in the country. We have more in-floor heat than Lambeau Field has at Lambeau Field. So
Whoa.
they heat the grass. for
Take
those
that.
winter games.
Well, gosh darn.
Yeah.
Oh, you
So-
Seahawks fan, get out of here.
Yeah.
I'm sorry. That was
Jim, it was like 5 games.
I know. Sorry, that was instinctive. Just anytime it comes up, I look at you.
But so then in addition to the building temperature on the machines, when you're machining, you're spraying coolant onto the part to keep the cutting tool lubricated and everything like that. But there's a lot of friction when you're cutting, and so it creates heat. And so that coolant gets routed through these machines called chillers, and those chillers actually control the temperature of the coolant, make sure that it's 68 degrees. So when it gets sprayed on the part, it's 68 degrees. And that way we keep all of the temperatures consistent from the metrology lab to the machine shop to inside the machines, the coolant that's being sprayed. And that way there's no variable. Like, for example, you don't want to have a machine that's spraying really hot coolant on a part, and the machinist pulls the part out and he measures and he's like, oh, it's good. And then he sends it over to metrology and it cools off and now it shrinks, and they measure it and they're like, no, it's too small.
Oh.
So we keep those temperatures really consistent so that we don't have that happening.
That's so cool. It's wild.